energy. So sweat is potentially a resource of non-invasive information. In fact, the community, the European community, has funded, but I don't want to talk about that because Jean Luprano, who is a coordinator, is here, has funded one of these projects, which is biotech, is a strap, which is going to the end right now, is probably handed in a strict sense. And so this is a sort of a textile integration with patches and sensors, etc., for sweat analysis. To my knowledge, it's one of the few existing, if not the only one, with such a goal. And but again, here is what you can do. You can make something, and which is, I think, was very successful in my opinion. You can do pH sensing, conductivity, others, by using textile, functionalized textile again. But you know, this is, I think it's beautiful. You make textile pumps. This has been done also in Dublin City University. So you can make this, but again, it's a first trial. That's, to me, is a big success from my personal point of view. And you can make sweat rate sensors. So in a sense, like you can make, maybe 40 years ago, a transistor or a vacuum tube before, but then you want to integrate that. And the integration is always a nightmare, especially for new things, because this is a patchwork of everything. Obviously, necessarily, cannot be different. The question is, can you go a little bit further in this direction or not? I don't know, but I'm sorry, but this is too high, but the idea is a full plastic, all polymer, microfabricated microsystem for sweat, whatever. I don't call analysis, because it can be something else. But anyway, it deals with different problems. I want to treat a little bit one by one quickly because time is passing fast. Obviously, the first part is sweat is not coming out where as much or as little we want. So how, it's not like putting a syringe in a vein, taking a sample, or collecting a urine sample. Sweat is a ephemeric thing. So sweat collection is a problem. I don't know, Jean maybe will talk about this afternoon because I don't know the detail, but sweat collection is a problem. As you can see, this is a, this is a chemical stimulation that is done. This is a commercial system. It's done periodically for drugs mostly, but also for a few pathologies, but is a chemical release of pilocarpine, which is a sweat stimulator, which has several drawbacks, including inflammation, etc. So it's not something you can use really in a continuous system. This is just speculation, but it's not. It's only speculation. I tell you, we are looking preliminary. All this is very preliminary. Is there a way by AC electrophoresis? Maybe you don't know, more of you, because AC electrophoresis is not electrophoresis at all. You don't need hundreds of volts. You need 2 volts. And is presently very much studied in microsystem for making micropumps. So the question here to me, and we start something quick, not much. Can I use electrophoresis, AC, from outside this complex system, to pump out what is sweat is already in the sweat duct? Okay. I don't want to say more in the sense that is a question. How can, when I collect that, I have to collect the sweat. I'm not talking about doing something physical. I'm talking about the older person or something which is not sweating massively, etc., etc. Anyway, this is a problem. I want to underline problem more than solution, or open some thinking in some area. Second, that's something I like a lot. This is very schematic. We are doing for something totally different. We're doing for a potential NSF collaboration with the United States, but it's artificial sarcomere. Okay, don't think about strange thing. Is actuation. So it's a microsystem, which to us is a micro pump. In a sense, the sarcomere is really a motor, an extension and release. But again, microactuators are something we look for several years, and they can be all plastic and all microfabricated. And there, I want to touch point by point. So the artificial sarcoma is a system, People think that the people which are not working, like the artificial muscles, they are not material. The muscle is a system. You need power supply, you need everything. But anyway, quickly going. Then this fluid, you have to do something with that fluid. Again, this is from my colleague in Linköping in Sweden. This is from NSF annual report. But I found this, there is some work which I found extremely interesting. Using, again, material, I will talk about material quickly in 2 minutes at the end. All this can be done by conducting polymer and other materials. And they are fully compatible with microfabrication. I will show you later. Otherwise, it seems to be, again, a patchwork. So this is a very interesting work which is done in Linköping, but also in other places, in Sydney, and also in Dublin. Is really change, you see this, you can change by a very tiny voltage difference the wettability of a surface of a conducting polymer, making hydrophilic, hydrophobic. And there are really nice movie, in which you can see drops really spreading all around. Like you can drive them in the circuits, like just switching electronically the wettability, hydrophobicity of these circuits. Like here in a different context. Yeah, I'm just to the end. Quickly. I don't want to talk about sensing. I've been talking about sensing forever. But things that analytic, synthetic, or whatever. Sensing is a different story. E-logic, that's beautiful, important, but that's recent work from Linköping and from us also. More recently is you can make electronic circuit by low voltage. This is work of Ole Inganas, again in Linköping, is made on a textile, but can be made like Berggren on a planar surface. And this is electrochemical transistor. So that's a technology which is very, very promising and which is going to be exploited by Acreo in Norrköping. Antenna, no problem. Textile antenna transmission. Quickly, okay, we have a microfabrication facility which is made of different tools. I don't have time now to say that the pressure assisted microsyringe. So there's a fabrication unit in which you want to integrate all this in a plaster. Our goal is to think about a plaster all made of plastics, not combining silicon, conducting polymer, silicone, polyurethane, whatever, in which all this function can be implemented. This is the wishful thinking, obviously, but we have concrete ideas. And so this is one technique, and just to show you this is something we realize now. These are capillary, this is more for tissue engineering, this is capillary tree. These are something we put electronic on that. All this will be a router for transistors. You can make a multiplexer out of this. And this is the base for making the plaster quickly because I'm running out of time. This is a second, is a variation. Through this technique, we can use a material. For example, use PDOT, which is a conductive polyaniline, polypyrrole, polyurethane. In principle, that's all the same. In practice, viscosity and other parameters force you to make a multi-integration. So that's a different technique. And quickly, again, you can do other things. This is hydrogel. And at the end, the last two slides, you can also, and we do laser ablation and also combination of the technique in a unique machine, which is now almost ready. So you can have 2 syringes for different material and 1 laser ablation for removing material with a submicron resolution by which you can do things like that. So that's all I have to say. Is probably even too much, but that's, you assigned me to a task which was very difficult. Thank you very much.
Okay, thank you very much, Danilo. I knew that your presentation will not match 100% with the title, but it was very interesting.